Hello students, welcome to EPG Pathshala. I am Professor P.N. Kotru from the University of Jammu. Today we are going to discuss about a module entitled Experimental Methods for X-ray Diffraction under paper Crystallography and Crystal Growth. Let us know what we shall learn about these X-ray today. Experimental methods, namely Laue spots method, rotating crystal method, and powdered crystal method are described. Applications of Laue diagrams to the determination of symmetry and structure of materials, orienting single crystals, and investigating distortion of or polycrystallinity of materials is explained. The principle of powdered crystal method is explained. Measurements of Bragg angle and interplanar spacings in crystal are discussed. The procedure of indexing powder patterns is also discussed. Rotating crystal method, its experimental setup, both for simple as well as modified ones, and recording procedures are described. The procedure of indexing powder patterns is discussed. Experimental methods for X-ray diffraction. X-rays have proved to be of great importance on account of the fact that they have many and varied practical applications, which may be summarily classified as follows. Purely scientific application, such as in crystallography, to analyze and determine the internal structure of crystals and investigate the perfection of crystals. Industrial application, which is also given a general name of radiometallography. Medical application, such as radiodiagnosis, known as radiography, and treatment, that is X-ray therapy. Here we will take up only scientific application relevant to crystallography for analysis of crystal structure. Experimental methods. The Bragg's law expressed by an equation n lambda equal to 2d sine theta for X-ray diffraction suggests that the diffracted beams can be found only when reflections from parallel planes of atoms interfere constructively, and that would happen if the Bragg condition is satisfied. In order to meet this condition for X-ray diffraction, it is required to provide for continuous range of values of either theta or lambda in an experiment devoted to analysis of crystal structure. The methods are Laue spots method, rotating crystal method, powdered crystal method. We shall now consider these methods slightly in more details. Laue spots method. Figure 8.1 shows experimental setup of Laue method. In this method, single crystal is kept fixed and a continuous or wide spectrum of X-rays is used. Figure 8.1 shows the experimental setup. X-rays from the source are made to fall on a crystal and films are appropriately positioned to detect the transmitted as well as back reflected radiation as shown in the figure. This method is used either in transmission, generally at small angles, or in reflection, which is popularly known as Laue back reflection method. On exposure to radiation, one finds spots on the film in directions and for such wavelengths which correspond to the conditions for diffraction. X-rays of short wavelength and carrying high energy are usually involved for transmission patterns. X-rays of longer wavelengths and lower voltages are used in reflection. An X-ray beam with continuous range of wavelengths can be obtained by using a bulb with anticathode and high tension of about 65,000 volts. One finds a series of spots arranged on an ellipse in a Laue photograph by reflection at the planes around crystal zone. The arrangement of spots, as seen in a typical Laue photograph of a simple cubic crystal, is shown in a schematic diagram of figure 8.2. Laue diagrams are used for determining the symmetry and structure of materials, orienting single crystals, and investigating distortion or polycrystallinity of materials. Thick samples can be used for back reflection method, which offers the advantage of higher resolution as compared to transmission method. Very fast diffusion transfer films and luminescent screens have been used, which to a very great extent shorten the exposure time required for Laue photographs. Films are being replaced by Geiger or scintillation counter techniques coupled with data processing equipment. The powder crystal method. All the methods, be it Laue method or rotating crystal method, require a single crystal specimen whose size is greater than microscopic dimensions. However, in a very large number of crystalline solids, individual crystals of the desired size as required for the rotation photograph either do not occur or are not available. All the method, such materials are readily examined by this method. This method was devised independently by Debye and Scherer in Germany and by Hull in America about the same time in 1916 and called powdered crystal method or powder photograph method. The principle of this method is as follows. Let a monochromatic X-ray beam be allowed to fall on a small specimen of the material which is ground to a fine powder. The sample is obviously in a polycrystalline form, which is an aggregate of extremely tiny crystallites randomly oriented with respect to a given direction, and as such, all possible orientations of all lattice planes are present in the powdered sample. There is bound to be a certain number of crystal grains which will be positioned with a given set of lattice planes making the correct angle with the incident beam for reflection to occur, while another fraction of the grains will have another set of planes in the correct position for reflection, and so on. Further, reflections are possible not only from the different set of planes but also in the orders for each set. The powder crystal method is the only technique which is readily available to all crystalline solids. The diffraction data, which depend on the lattice parameters, are unique for a given material and therefore can be used for its identification. To identify a human being, we make use of his fingerprints. In the same way, diffraction data of powdered crystalline samples are unique and becomes a means of their identification. Let us consider a monochromatic beam of X-rays which is incident at Bragg angle theta on a set of lattice planes with interplanar spacing small d in some particular crystallite, so that the Bragg condition 2d sine theta equal to lambda for the above set lattice planes is satisfied. Considering the diffracted beam from a large number of randomly oriented crystals and take into account the diffraction from the planes with the same interplanar spacing as the first one, the locus of the diffracted beams would lie on a cone with half apex angle 2 theta because the angle between the incident beam and the diffracted beam is 2 theta. The situation is shown in figure 8.3. The diffracted beams from other sets of lattice planes with different interplanar spacings, say D1, D2, D3, D4 and so on, would lie along different cones with different half apex angles 2 theta 1, 2 theta 2, 2 theta 3, 2 theta 4 and so on. Since the incident beam direction is the same for all these lattice planes, the cones would be coaxial. So the different beams from different set of planes HKL would all lie on a circular cone. If the same is recorded on a flat plate perpendicular to the incident beam, each diffraction from HKL planes would appear to be like a ring or halo around the central spot as is shown in figure 8.4. Different film placements are possible. If the film is placed normal to the incident X-ray beam beyond the powder in figure 8.3, the powder diffraction pattern gets recorded in the form of concentric circles or circular rings as is shown in figure 8.4, and the theta values can be easily evaluated. However, this type of film placement has a disadvantage, and it is that several powder lines with 2 theta greater than 90 degrees, known as high angle lines, do not get recorded. On account of this limitation, this type of film placement, that is the flat film, is not used. To overcome this limitation of a flat film, a cylindrical film strip is used so that all the lines corresponding to 2 theta from 0 degrees to 180 degrees get recorded on the film as shown in figure 8.5a. This technique is due to Debye-Scherrer, and the camera is named after them as Debye-Scherrer camera. On unrolling the film, one finds that the pattern on it is of the type as shown in figure 8.5b. The diffracted rays, which are at small angles, make arcs around the central spot on the film. Those which get diffracted through 90 degrees and the corresponding trace on the film is a straight line. The material to be investigated is ground into a fine powder which is then stuck on a hair by means of gum. It is then suspended vertically in the axis of a cylindrical camera, which enables sharp lines to get recorded. The photographic film fits around the inner surface of camera, covering practically the whole circumference in order to collect beams diffracted up to nearly 180 degrees. The X-rays, after falling on the powdered sample, passes out of the camera through a hole cut in the film in order to minimize the fogging produced by the scattering of the direct beam. The crystal structure is deduced from the arrangement of the traces and their relative intensities. Taking Bragg equation, 2d sine theta is equal to n lambda, and differentiating this equation leads to del d sine theta plus d cos theta del theta equal to 0, n and lambda being constants, or del theta by del d is equal to minus tangent theta upon d. When the angle of incidence theta approaches 90 degrees, del theta by del d becomes very great, which means that Small variations in d produce large variations in theta. Measurement of Bragg angles theta and the interplanar spacings d. In order to find d values, it is required to measure theta values. To this, the film is placed flat on a viewer with a linear scale fitted thereon. The film with diffraction lines is placed on the viewer, which has illuminated background. The position of diffraction lines are noted starting from one end along a line passing through centers of the entry and exit holes. There are two ways in which one can make measurements. One way is to note the readings R1 and R2 of the two arcs corresponding to a diffracted cone. R1 minus R2 is then the linear distance between arcs corresponding to one set. This gives the linear distance 2r from which theta is calculated. The second way is to measure r directly. This is done by locating the center of the direct beam, which coincides with the center of the exit hole and so corresponds to theta equal to 0 degrees. Position of each arc from this point provides us the value of r. We know the radius small r of camera. Having determined the linear distance capital R through measurement, Bragg angle theta can be calculated by using the relation 4 theta equal to twice capital R by small r, or theta is equal to capital R by twice small r radians, which is equal to capital R into 180 by 2 pi r degrees. The above relation easily derivable from the diagram shown in figure 8.6. This method is applicable to any kind of crystalline matter. Since it does not require single crystals, it is very valuable and of great use in the investigation of metals and alloys, ceramics, and any material in the polycrystalline state. Figure 8.6 shows conversion of linear distance on the film into Bragg angle. In the equation theta equal to capital R into 180 by twice pi small r, the term 180 by pi is equal to 180 into 7 by 22, which may be taken as 57.3. So if a camera of diameter 2r equal to 57.3 millimeter is used for recording powder pattern data, 1 degree in angle theta would correspond to 1 millimeter in capital R. This way, the geometric conversion of capital R into theta is simple and straightforward. It is important to bear in mind that while making measurement of linear distances and then converting them to theta values, a distinction is required to be made between low angle diffraction lines and the high angle diffraction lines. Scattering of radiation from the air in the camera results into the background intensity. This background intensity is maximum near theta equal to 0, which corresponds to center of the exit hole of the camera. Because of this, the film near the low angle side has more of background blackening. The second distinguishing feature of low-angle diffraction lines concerns the resolution of lines corresponding to, say, K alpha 1 and K alpha 2 components of the K alpha doublet for CUK alpha radiation, which is generally employed for powder diffractometry. CUK alpha is composed of CUK alpha 1 with wavelength lambda equal to 1.54050 angstroms and CUK alpha 2 with wavelength lambda equal to 1.54434 angstroms. As a result of this, every diffraction line is a doublet corresponding to these components of K alpha 1 and K alpha 2 wavelengths. For a camera of diameter 57.3 mm, the doublet appears as a pair of two closely spaced lines which can hardly be resolved and as such appear as one thick line. The situation is different in case of cameras with larger diameters. The two components arising from K alpha 1 and K alpha 2 wavelengths get better resolved only at the high angle side, where the separation between the two Bragg angles is wider, and so the doublet can be easily identified. Once the Bragg angle theta is found out, application of equation 2D sin theta is equal to lambda yields d values, that is the interplanar spacing. The interplanar spacings are related to the lattice constants A, B, C through Miller indices HKL by the equations given in Module 6, Section 6.3.1 for various crystal systems. We shall take the example of a powder photograph of a cubic crystal taken on a camera of 57.3 mm diameter with CUK alpha radiation, where lambda is equal to 1.54 angstroms. From 2D sin theta equal to lambda, we have sin square theta is equal to lambda square upon 4D square. For a cubic crystal, D is equal to A upon under root h square plus k square plus L square. Sin square theta equal to lambda square upon 4a square into h square plus k square plus L square. Let us put h square plus k square plus L square equal to capital N, where capital N is an integer. Therefore, sin square theta is equal to lambda square upon 4a square dot n, or sin square theta by n is equal to lambda square by 4a square. The linear distances of the diffraction lines are measured and theta values determined for every line. For these theta values, we determine the sin square theta values. Division of sin square theta by different values of integers gives the possible n values. A list of possible n values is prepared, and the values of sin square theta by n determined we should have a common factor lambda square upon 4a square as per the above equation. Suppose that common factor turns out to be sigma. Substituting for lambda is equal to 1.54 angstroms, say, for example, one is able to get the approximate value of lattice parameter small a. This procedure is adopted for a few low angle lines and then for high angle lines. For crystallographic characterization of any material, it is extremely important to determine lattice parameters very accurately. That is done by taking measurements on the diffraction line corresponding to theta equal to 90 degree. However, theta is equal to 90 degree corresponds to diffracted beams which are directed back into the incident X-ray beam, making its recording impossible. So one tries to make measurements as close to theta equal to 90 degrees as possible, or extrapolate the measured d values to theta equal to 90 degrees. The parameters required to be determined are the lattice parameters and the indices of various lines. While it is relatively simple for crystals of higher symmetry, it is quite complicated for the crystals of other systems. Indexing of powder photograph. The procedure of indexing of the powder pattern is based on the type of crystal classes that one is dealing with. It depends on the following: substances whose unit cell is known, substances whose unit cell is not known. For substances in category 1, indexing is rather simple, whereas for the category 2, indexing is not that simple. For the latter type, trial and error methods are adopted for assigning indices to the powder lines. Let us first know very briefly about the method of indexing powder lines of those substances whose unit cell is known. There are two approaches, analytical approach and the graphical approach. In analytical method, for substances whose unit cell is known, the assignment of the indices is done by comparing observed theta values with those of the calculated ones. From the powder pattern, values of sine squared theta are found. On the other hand, sine squared theta corresponding to various HKL indices from the known unit cell parameters calculated. Through comparison of the observed values of sine squared theta and the calculated values of sine squared theta, the values that tally correspond to the HKL indices. Taking simple cubic crystal as an example, the interplanar spacing d is given by d equal to a upon under root of h square plus k square plus l square. 2d sine theta equal to lambda, and so sine squared theta is equal to lambda square upon 4d square. Therefore, sine squared theta is equal to lambda square upon 4a square into h square plus k square plus l square equal to lambda square into capital N upon 4a square. All possible values of capital N are used to calculate set of sine squared theta. Values from this expression. The possible values of capital N equal to h square plus k square plus l square for the cubic lattice are provided in the literature. It may be of interest to know that certain possible values of capital N like 7, 15, 23, 28, 31, and so on are forbidden. If the substance does not belong to any of the cubic systems, one has to adopt a different procedure. For example, in the case of tetragonal system, the following equation between sine squared theta and HKL indices is used. Sine squared theta HKL is equal to lambda square upon 4a square into h square plus k square plus lambda square upon 4c square into L square. Let us put lambda square upon 4a square equal to capital A and lambda square upon 4c square equal to capital B. Sine square theta HKL is equal to capital A into h square plus k square plus capital B into L square. To calculate various values of sine square theta HKL of different sets of HKL indices, a table with two sets of values, one for the first term containing possible values of capital A and the other for the second term containing possible values of capital B. Tables giving possible values of sine squared theta are available in the literature. A particular sine squared theta HKL value is obtained by suitable addition of the values from the two sets. The calculated sine squared theta HKL values are then compared with the experimentally determined values, and those which match are taken for assignment of indices H, K, L to the observed lines. Similar procedure is followed for indexing the lines in the powder pattern of trigonal and orthorhombic systems. The equations to be used in case of hexagonal and rhombohedral systems are sine squared theta by HKL is equal to lambda square upon 3a square into h square plus hk plus k square plus lambda square by 4c square into l square. For orthorhombic system, the equation to be used is sine squared theta HKL is equal to lambda square upon 4a square into h square plus lambda square upon 4b square into k square plus lambda square upon 4c square into L square. For monoclinic and triclinic systems, it is convenient to use expressions in terms of the reciprocal lattice parameters A star, B star, C star, and alpha star, B star, gamma star. instead of direct lattice parameters, and the expressions for monoclinic and triclinic systems are respectively given as follows. Monoclinic system: 1 upon d square is equal to h square a star square plus k square b star plus l square c star square plus twice LH C star A star cos beta star, the unit cell having been defined such that B axis is perpendicular to the A and C axes. Triclinic system: 1 upon d square is equal to h square a star square plus k square b star square plus l square c star square plus twice h k a star b star cos gamma star plus twice k l b star c star cos alpha star plus twice l h c star a star cos beta star. The said procedure is the analytical one. However, graphical methods are also followed. In this method, curves are drawn between the interplanar spacings, that is the D spacings, and the cell dimensions for those whose unit cell is known. The experimental D spacings are plotted and compared directly with the theoretical curves. The matching between the theoretical and experimental curves is done, and indexing of the powder pattern is achieved. The rotating crystal method. The powder crystal method is the most useful and feasible method obtaining information concerning a material which cannot be made available as a single crystal. However, it is not suitable for the determination of internal structure on account of difficulty in indexing. Therefore, the rotation and oscillation techniques are used, provided the material becomes available in the form of a single crystal. This method enables measurement of lattice constants and indexing of reflections quite easily. The intensities of individual reflections are conveniently measured, which enables us to determine the crystal structure. The rotating crystal method was devised by Scheibold and Poliani. Its principle is based on the fact that if a crystal is rotated slowly about a fixed axis, a large number of planes will successively come into the reflecting positions, and the diffracted radiation onto the photographic plate or film in the form of a pattern of spots, popularly called as rotation photograph. In one type of technique, a photographic plate, say capital P, is kept at a distance of a few centimeters from the single crystal capital C so that its plane is normal to the incident beam. The crystal is then rotated about its predetermined axis, say C axis. The beams reflected from all planes parallel to this axis lie on the surfaces of a family of cones whose axes coincide with the axis of rotation and whose vertices are at the crystal. The cones on intersecting the photographic plate positioned parallel to its axis result into a series of hyperbolas. The experimental setup is shown in figure 8.7. Shows figure 8.7, which is the experimental arrangement for rotating crystal method. In a slightly modified technique, see figure 8.8a, the reflected beams from crystal C are registered on a photographic film P, which is bent in the form of a cylinder whose axis is along the axis of rotation of the crystal. In this type of setup, the reflections from all planes which are parallel to the axis of rotation lie in a plane normal to the axis. This plane cuts the cylindrical film in a circle. On unrolling this film, the reflections are found to get registered on a horizontal line containing the registration of the incident beam. The registration of spots is seen as a series of hyperbolas above and below the horizontal line. These lines have been named as layer lines and look something like shown in figure 8.8b. Production of layer lines in rotation photograph on flat film and cylindrical film is shown in figures 8.9ab. Here the crystal is rotated about C-axis as shown. Planes which are parallel to C-axis will reflect rays horizontally, forming spots along a horizontal row along with the central spot. This is called as zero layer line. There will be other reflections which would make an angle with the horizontal row of spots. Accordingly, the lines are named as zero layer line, first layer line, and so on, as is shown in figure 8.9. With complete rotations of the crystal, large numbers of spots recorded on the film, it is therefore customary to rock the crystal back and forth through an angle of only 30 degrees. It limits the spots on film to those of certain indices. The angular rate of rocking is however kept constant. From the distances between the layer lines, the lattice spacing in a direction parallel to the axis of rotation is determined. Taking rotation photographs with rotation of the crystal about all the three axes A, B, and C separately is a method which is helpful in the determination of size of the unit cell. Weissenberg modified the technique in which the crystal is rotated through 180 degrees and back again continuously while the cylindrical camera fitted with the film moves at a constant speed forwards and backwards in the direction of the axis of rotation. The camera motion is so synchronized that its position corresponds to a definite angular position of the crystal as its rotation. It enables to accurately to index the spot on the film by noting its coordinates, providing both the angle of reflection and the position of the reflecting plane. A cylinder made of a metal with a suitable and a few millimeters wide slit is placed in between the crystal and the film in a position that allows the spots corresponding to only one layer to pass through it. In other words, the metal with an annular opening, when suitably adjusted, allows only the diffracted beam for the second desired cone to get through while blocking the diffracted beams corresponding to other cones. The X-ray diffraction technique described above lead to determination of lattice parameters. One also needs to find out the structure, that is, the position of atoms in the unit cell. For the determination of the crystal structure, accurate measurement of the intensities of a large number of Bragg reflections is necessary. Crystallographic measurements are nowadays done on a computer-controlled diffractometer. Let us now summarize of what we have discussed so far. In this module, we have discussed experimental methods for X-ray diffraction. The methods include Laue spots method, rotating crystal method, and powdered crystal method. Experimental setup of Laue method is schematically illustrated and described. The arrangement of spots as seen in a typical Laue photograph of a simple cubic crystal are schematically illustrated and described. Use of Laue diagrams in the determination of symmetry and structure of materials, orienting single crystals, and investigating distortion or polycrystallinity of materials is described. The powdered crystal method as a valuable tool, particularly for materials which are not available in single crystal form, is explained. Procedures involved in the measurements of Bragg angle theta and interplanar spacings in crystals are explained. The procedure of indexing of powder photographs, both for substances whose unit cell is known as well as substances whose unit cell is not known, are described. Experimental setup for rotating crystal method, modified rotating crystal method are illustrated and described. Production of layer lines in rotation photographs are discussed. Thank you.